We're now at a point then with the nebular theory that we're over here. We've collected enough evidence to turn our hypothesis, tested it quite thoroughly based on what we could observe in our own solar system and in other nebulae, that we're content to now call it a scientific theory. But we're now at this stage here where we're still continuing to make new observations, and we're going to see how those impact our nebular theory. To further test nebular theory then, if our problem was that it's based on only a single example of a solar system, then what we need to do is we need to predict something that should be observed about other solar systems if the nebular theory is correct. And then we simply need to find other solar systems and observe them to see if what we predicted using deductive reasoning about them is actually correct. Okay? In other words, we're trying to come up with a consequent from a deductive argument from our theory, and then either affirm the consequent to give us a reason to believe the hypothesis, or deny the consequent, and that gives us reason to doubt the hypothesis. So what can we come up with? Well, if nebular theory is correct, then we should observe that in all other solar systems, you could come up with a number, but let's look at one very, very significant one. Remember that we had used the kinetic molecular theory to flesh out our understanding of planetary formation, particularly the second point, that the speed of the particles is directly related to the temperature. And when we added this idea into nebular hypothesis, it explained for us why we have the small rocky planets all close to the sun and the large gas giants far from the sun beyond what we called the frost line, the point at which the temperature drops low enough that most materials are now frozen into ices. What that also meant is that it affects, as kinetic molecular theory tells us, it affects the speed with which the particles are moving. So in the inner solar system, where the temperature was high, the gas particles were moving too fast to be trapped by the growing accreting planets, and the planets ended up being made only of rock and were therefore quite small. On the other hand, in the outer solar system, where the temperatures were much lower out beyond the frost line, the gas particles are moving very slowly. They could be held by the gravity of the accreting rocky planets, and they built up these massive atmospheres through this positive feedback loop to end up as gas giants. So if all that is correct, and it's now a part of nebular theory, then we can make an observable prediction. And the observable prediction is this: if nebular theory is correct, then gas giants in all solar systems should always be found far from their parent star. So in the next video, we'll see whether this prediction was actually observed.